Hello everyone, November 23rd. Alright, happy Thanksgiving. Alright, this is what we're gonna do. So we're gonna do this and we're gonna go back to this. Not this one. Yeah, I'm not ready for this one. Yeah, we're gonna code this solution. Sorting a binary search. I think I might understand, but not 100% sure. But hey, this one definitely works, right? This solution. We're trying to sort X and sort Y. Yeah, the other one is different. But anyway, maximum number of coins you can get. There are 3n piles of coins of varying sizes. You and your friends will take piles of coins as follows. In each step, you will choose any 3 piles of coins. Of your choice, Alice will pick the pile with the maximum number of coins. You will pick the next pile with the maximum number of coins. Your friend Bob will pick the last pile. Repeat until there are no more piles of coins. Give an array of integers pile where pile I is the number of coins in i's pile. Return the maximum number of coins that you can have. So basically 3n, so you can take n times, right? N steps, and each step you will choose any 3 piles. So you can choose any 3, and you will always pick the middle. And we want to ask what will be the maximum number you can pick, which means each time you will want to pick, you can never pick the largest no matter what. So you want to pick the second largest, and you want to give Bob the smallest. Right? So in this case, you pick 2, 8, 7. So you sort it first. Right, we sort this one first. It is 1, 2, 2, 4, 7, 8. So we pick. Largest always goes to Alice, and smallest always goes to Bob. So you just pick the second largest. That's the first pick. Next one, you can never give 4. So 4 goes to Alice, so you got this. So you got 9. We're gonna try this one. 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? So you get this. You get this, you get this. That's 18, right? That should be the best way that you can do it. Because every time, again, like the best you cannot pick. So the maximum you can pick is the second largest one. And once you pick the second largest one, you cannot pick the third largest one because that will go to Alice again. So you pick the fourth largest one, which just means we just need 2 pointers. Ooh, look at that. 2 pointers, one goes to Bob, the other goes to Alice, and then you will pick this one. And then I will move forward 1, J will move forward 1, 2. And you do it again, So it's kind of greedy. And let's give it a crack. Yes, what's the crack, horse? What's the crack, horse? All right. Let's do this. So first of all, sort the piles. Smaller than J. We shall actually have a res. Okay. Res plus equal to piles j minus 1 I plus plus j minus minus. Can I do that? I don't think so. Oh my god. We can do this. But that's not explicit. I don't like it. So what we're gonna do is j minus minus. Might as well just equals minus equal to. It might be wrong, but I don't see why. I think greedy will work. Yeah, greedy works. Always pick the second largest for myself at each step. Man, I'm still feeling bloated. Oh, why you always say oh when? It's not oh when, man. It's log n because you sorted it. Yeah, this one works too. Me too, because the cheat day thing. All right, so we're done with this. It's an easy problem today. Yeah, let's go back to this. So, if I understand correctly, we have two things to do for this problem. First, we are going to sort. So again, it's x and y, right? So we have x, right? And then we have y. And what we do is we sort x from large to small. It's almost already sorted. So we just use this. Yeah, so we just need to sort this 2, 1, 5, and 9. Right, we sort x, and then we sort the query, also from large to small. So the queries will be, 4, 1, 2, 5, and a 1, 3. So the benefit of sorting both is that once you get rid of all the queries with x larger than the biggest x, anything else coming in, we know there's always an answer. So we don't have to worry about x anymore. So that is the benefit. Okay, so x is easy to resolve. We just binary search this thing. Done. We'll get x. Well, we don't even need to binary search x. Like I said, as long as the x is we can actually run an initial phase, get rid of all the queries where it's too big, right? We get rid of all the queries where it is too big. The query x is too big. So get rid of them. And then for each of them, we don't have to worry at all. Then what we do is we have a query, which is good. Then we need to look into the y. Okay, we need to figure out what y is it going to be. And the y we are going to do is sort it, not sort it. We are going to say, increasing, right? Because we want to find a y because x is going to the left, right? And you want to get, yeah, so y is going up. Y is increasing. And then x plus y is decreasing. So in that case, right, so if we have a big y, doesn't matter. If we have a big y, if we have a small y, yeah, if we have a small y, right, then since x is decreasing, so x plus y is small, so we can just put it there. But you said y should be increasing. No, if it's a small y, we ignore it, right? Because it does not work if y is small. A small y does not work. We don't want a small y, right? Because x plus y is... So we want a big y, right? If y is bigger than the previous one, right? If y is big, then we check x plus y. If x plus y is small, we just put it there. That's fine, because we want x plus y to be decreasing. If x plus y is big, then we will pop, because it's a monotonic decreasing array on x plus y while maintaining y is increasing. The benefit of this is for each query you have, we'll check y and we'll binary search y, right? And once we binary search y, what we get, the binary search result, is going to be the biggest x plus y you can have, because x plus y is decreasing. Yeah, that is the deal. That is the deal. So we are going to code this in Python. So we're gonna reset this. I'm still proud, very proud of the segment tree solution. Very proud. Every time I do segment tree, I'm proud. You're the best in the world. How weird. It is very effective. You go out everyone time. Ja. Straight into the bed. 这边我给你磕头。 People in the comments are saying so too. Oh shoot. Alright, we're back at it. Ah. Let's do this. Oh my god. I still have Thanksgiving food in my belly. Alright, so first things first. What we have is going to put num, so xy. Okay. Sorted. XY. Oh no. Zip. Nums 1, nums 2. Okay. So XY, we're done. Now queries also need to be sorted. And we say sorted queues. Sorted for I, XY, enumerate queries. X, Y, I. Okay. Now we have both. Then what we're gonna do is res shall equal to, it doesn't matter, times len queries. Okay. Then we're gonna go skip all the x, right? We should say while, no, I is equal to 0. So while I is smaller than sorted len queries. Nope. While I and sorted queries I 0, which is the x, right? While this is larger than xy 0, 0, I plus plus. So we can actually add a comment here. Skip all the queries whose x is larger than the biggest x, whose x is larger than the biggest x. Bless you. Qx. Well, we need to also say res I minus 1. Okay, now we have what we want, right? Now what do we need? We need a stack. Now while I is smaller than len queries, we're gonna get to the end of it, and each time we know it's good. X is always good, right? So we're just gonna check on the Y. So what we're gonna do is if Now we're gonna say qx qy qi equal to sorted qsi. Okay, if query y is larger or equal to if not stack, or query y is larger or equal to, so what you're gonna put in a stack? Y and x plus y. Okay, larger or equal to stack -1 0. Probably should put here stack I is equal to y x plus y. Shouldn't you also get an xy for that? Yeah. You should also get xy for that. Okay, that's fine. So we're gonna go back and say j equal to this. So I handle this, right? Yeah, if the qy is smaller than the stack, right? If qy is smaller, query y is smaller, then it's basically useless. We don't want it. We don't want it. We want a y to be increasing, because a smaller y will always give me a smaller x plus y, which is useless. So if y is bigger, then we shall say while stack and stack -1 1. This is x plus y. If it's smaller or equal to, right? Smaller or equal to, we can pop. Doesn't matter. Ooh, should we pop though? Smaller or equal to. So y is bigger. If a bigger y, and then we get an equal. If y is bigger and it's equal, it's possible. Y is bigger and we get it equal. If we pop, then we might have a smaller one. No, we should not. We should leave the equal ones on x plus y. But what if y is equal? Now, if y is equal, that is interesting. If y is equal, so a binary search, we need to keep the bigger one. So if it's equal, remember, y is going up, right? Y is going up. So if y is equal to the previous y, and we want the stack to be bigger, so if the stack is now bigger, it's fine, right? Which means the equal, we can just pop. Yeah, if I have a bigger y, which give me, if I have a bigger y, which give me the same value on x plus y, I can always pop. It doesn't matter, because the bigger y will keep. If I have equal y, right, and now we have equal, we can pop. Doesn't matter. So we'll always pop. Yeah, which means if it's smaller or equal to the current j, right? So xy j plus xy, xy j 0, xy j 1. Right, so the current query comes in. Query is larger or equal to whatever the previous one I have. Right, the query is larger than the previous one I have. Then, yes, if the query is smaller, then we just directly go for the binary search. Exactly. If the query is smaller. Remember, white is going up, right? So if the query is smaller than the top of the stack, we don't add new y to it. We just binary search, right? If the query y is larger or equal to, then we check, right? But what if y is equal to, and then your value is actually smaller? Do we push it in? We do bisect left. Well, yeah. Okay. So if the stack is smaller than current j, we try to put the current j in. Shouldn't we go through all the j in? I'm thinking, how do we get x, y in? And why are we doing this way? Why can't we just pre-process the xy directly? Okay, I'm gonna change this thing. So I do the stack and 4. While stack and stack -1 0 is no -1, but we want to keep the y big, right? So while stack if not stack or y is larger than the previous one, then we say, and we check one smaller or equal to x plus y. Stack.pop. Right? If y is larger equal to, and then you go to the stack. If x plus y is larger than the previous, I just pop. Alright, go back again. Until I cannot. Going to the end. And then stack dot append y x plus y. So it goes through the whole thing. We'll create a stack with y. Create the stack where y's are increasing and x plus y decreasing. Now we do we skip, right? We do again. Now we have the query. Okay, then we just directly query. We don't have to worry about x, because x always works. So we just need to worry about y, qy. That's not I. It's sorted QSI 2. Okay. So this is QI. And then we just say index shall equal to bisect left stack QI key equal to lambda tuple top what? Y are increasing, so 0. Okay, your boundary is such. And then if index is smaller than len stack, right, then we can find something. Because y have to be bigger, and then we do bisect left, so yeah. Then res qi shall equal to stack index 1 else -1. And I'll return res. Forgot to handle this. What do you think? Honestly, I have no clue. So when I test it, first one's not right. So let's first check on the stack, see if the stack is correct. Stack is just 910. That is bonkers. Oh yeah, that was wrong. Reverse, forgot. Oh. Yeah, shoot. It's okay, it's okay, it's okay. What we need to do is just we will go and make it into a no. How do we go left? Do this. There we go. Okay. So now I reversed it. How come it's still 910? Oh, because yeah, I don't like to use yank. I like to use this, so I can delete however I want. And do this. Oh, I do use XY. Damn it. Huh. Yeah, I guess we do use it. That's cool, that's cool. It's alright. So we do XY. You gotta be kidding me. Let's see, what's XY? Yeah, XY is right. Oh, it is right. Because the last one's big, so it eliminates everybody. It eliminates everybody. Maybe I cannot do it this way. I have to go one at a time on the query. Let me think. We have to check X. Right? So if X is too big, then the current, then we try Y. That makes more sense now. So none of these nonsense. So we should go for the query one by one. Okay. If we need to do the right, we do this, and we say if QX is smaller than XY I, zero, right? So if the current one is smaller than, then we need to add, and if it's bigger than, then we don't need to consider any of the current. We can, if the QX is larger than the current XY, right, then because X is going down, you always look to the left of the X. You always look to the left of the X. You don't keep looking. It's only when it's smaller than the current, and you can keep looking. Maybe there's something more that you can get. Okay. So that's I. Then you can check, the next I. Maybe it's a while. While it's smaller, then we add it in. While it's smaller or equal to, we add it in. Okay, how do you add it in? Well, depend on the Y, right? So if not stack or stack -1, 0 is smaller or equal to xyi 1. So y is bigger, so this is the chance. So we can add, but before we add, we have to make sure that x plus y is decreasing. So while stack and stack -1, 1 is smaller or equal to. Yeah, equals fine, I think. Smaller or equal to xy I 0 I 1 stack dot pop. It works because if the y is equal, okay, if the y is equal, then this is not going to happen because x goes down and then y is equal to the previous one. So x plus y is either equal or smaller. If it's smaller, we just attach it, right? If it's equal, we also attach it. So basically we can have duplicates, which is fine. If y is bigger, then this is big, then we pop, right? If it's big, we should pop because it doesn't matter. If it's small, if this is small, we shall just append because monotonic decreasing. Yeah, so it'll be pop. And then we'll go through this. Once we're done, now stack. Okay, this is update the stack. Once we're done, plus equal 1, right? So for the current x plus y, we try to add it. Once we're done, x1 plus y goes back up. So we have to also do this. I is smaller than ln xy. Okay, so I plus equal 1. Try the next one. Once it doesn't work, okay, once it doesn't work, so xy now is larger than the, okay, that's when we are going to do index, okay, and the query y, and then we do all that, and we can do same. All right. We can find something, then we can update. Else, this is equal to 1. Right, once we're done, we go check the next one. And at the end, we return. Oh, that's even worse. What the hell? All right, let's check. XY, correct, sorted QS. correct. Yeah, we probably just put it out. That's why. So for the 4 comes out. I is smaller, that is correct. Qx is 4, smaller equal to xy, yes. Not stack. So I'll stack, no. Oh, I didn't add. Sorry. xy I1 xy I0. This is just really not intuitive, because every time I type this I have to quit it and then go for the next one. Now this one's right. Now they're all right. So we'll go back to this, comment them out. Yeah, I think this JK stuff I'm still trying to figure out. Thank Lord I checked. Okay, so what do I say? This is inspired by the solution. We shall put the name of the solution. Some Python solution, I remember. Sparse table. This one. So the idea is to sort xy and query in descending on x. Then create a monotonic stack which holds y and x plus y such that y is monotonic increasing while x plus y is monotonic decreasing. One major trick is to go through query one by one, and for any query whose qx is smaller, right, than the x encountered so far, we add more xy to the stack. Yeah, this is very important. We add more qxy to the stack. Right, this ensures that any qx is only checked against the xy that have larger x's than it. It's like here. If qx is larger, then we just go directly binary search. Is this right? Nope. I must have done something wrong. 142. All right. 89, 85, 53, 32, 75, 48. These are good. Should be 75 coming in, right? 75 is smaller or equal to xy. I 0, yeah, because 75 is smaller or equal to 89. And then if not stack, so we stack or append 53 and 142. Then wait, hold a second. Okay, fine, and then we go back up. Qx smaller or equal to xy. Yeah, so we have 85 and 117. Right? Oh, but y is not right because y is smaller, so we just add and with binary such query y48. We should have 53 and 32. No. Why should be increasing? Why should be increasing? Why? Right? Y is increasing, but your y is not increasing. Because we have a smaller y, you still put it in. Yeah, I think I know. Line 12. I think should be inside. It's only when we have a bigger and then we do it. If we have a smaller, we just ignore it. Yep. So this line. Yep. That's right. And run as fast as by the segment tree, but we got this. It's pretty hard, man. It's pretty hardcore. Okay, so we got this 2 solutions. This question should be left, untouched. But tomorrow I'll solve this one again. Let's see if I remember. I don't remember at all. Man. I don't remember this one at all. It's okay. It's okay. All right, that will be it for today.